So let's type that in, shall we? Y equals, clear everything that's in there. 450 bracket, 0.5 bracket, and like look at that. That's, oh, you can see. The exponent is very, very ugly, right? So I always try to come up with a few questions that are like, what? So that if the province decides to do something sketchy, right, then you're like, no, I've seen that. I don't have to worry about it. But the exponent itself is a fraction. So what I would do is I would go hat, right, hat button, and then I go brackets. Instead of y, so this is also tricky, instead of that y, we always use the x variable, right, for the variable that's on the right-hand side. And then we go divided by 5.73. That's how I would enter it. So hat, brackets, I would put a bracket around this exponent itself. Okay? And that's what it should look like. Before we graph, is this an exponential function? Yes. How do I know that? Because the variable is in the exponent. Is this increasing or decreasing? Decreasing because b is less than 1, right? So I know it's this because b is between 0 and 1. And what is this y-intercept going to be? 0, 450, right? So there's a lot of things that I already know just by looking at it. So I'm going to attempt to graph this. Let's see what happens. Oh, I actually see something, right? This could have just been the luck of the draw. So I'm going to try to be in your shoes here. Zoom standard. You press zoom, then standard, nothing. And I know that because how high up the y-axis do I need to be minimum? 450, right? So let's try zoom fit. Let's see if you're stuck. This is just if you're stuck, right? Zoom fit. And there we go. At least we start seeing something. We don't really care about this very much. So let's adjust the window a little bit. Window, instead of -10, I'm just going to go -1 for my x min. For my y min, I'm also going to go, because it's a big number here, remember, zoom fit, try to fit this thing. So I'm going to go -10 on the y min. So x min, y min, I'm definitely going to go negative there. Hit graph again. And there you have it. So for now, I'm going to leave it there. For now, that's as good as it's going to get. See what else the question is giving me. Let's see what the variables represent. So this is carbon-14 is one of the isotopes used to determine the age of organic material. Its half-life, it has a half-life of 5,730 years. You know it's decay, you know it's decreasing because of the word half-life. Okay? The units will be in thousands of years. For example, 5.73 thousandths of years for this one. So you basically just divide that by 1,000. Where C is the concentrations in ppm, do you guys know what that means? Parts per million. Right? That's how you measure concentration in the air. Parts per million, like carbon, parts per million. And Y is the years in thousands of years. Okay, so we're going to highlight that. Of the sample. Enter into Y as given. Okay, so what we know is that H is always our X value, right? Like whatever is on the right side of the equation is X. And C is the concentration. So we know now every single point on this graph is always H followed by the concentration. H is in thousands of years, okay? It says here, make a graph of this equation for a time of 30,000 years. How many thousands is this? It's 30 thousandths, right? So in this case, we would just divide this by 1,000, and that gives us 30. So that's what we would want to enter, right, into x, basically. Or that's how far along the x-axis we want to see. Let's adjust our window accordingly. Okay, so we go graph, I'm going to go window, and my x max, I'm going to go to 30. I'm going to go a little bit past 30 because I want to see a little bit further. So how about we go to 40? And there we have it. Okay. This is a little bit overkill. I don't need to see so far up the y max, so I'm going to reduce that. I'm going to go window, y max. I'm going to go maybe 1,000 only instead of 1,500. Just to make it, to customize it a little bit to our word problem, okay? Because we don't care about the other quadrants here. So let's make this graph all the way to x is equal to 30. In fact, I'm going to do a little bit of preliminary points that are going to help me graph this. Points to graph. Which one do I know for sure just by looking at the equation? 0, 450, correct? That's the y-intercept. And I'm going to find another one. I'm going to go second trace x is equal to, and I'm going to find the y value. So if x is equal to 30, let's figure out what the y value is at that point. Second trace value, x is equal to 30, enter. I get 11.94. And my suggestion would always be, if this is 30, try to find another point somewhere halfway through. So I'm going to say x is equal to 15. When x is equal to 15, what is y? Just to help me graph this thing. Second trace 1 for value. I'm going to go 15. That's 73. 7331. That is good enough. 3 points is pretty good for your graph. So let's go ahead and do that. I'll have a ruler here. Most of the time I will give you a grid. So we're supposed to make the graph. Here we go. And remember, you need the axes labeled and units attached to them. So this is the age and thousands of years. Basically just go and see what are the units that I'm given, and that's what you paste in here. Okay. And up here it's concentration. In ppm. Would it have made a difference whether or not you know what ppm is, if you knew what ppm was? Not at all. So they could say, like, any unit they throw at you, you should still be able to graph it. Normally they keep it simple, but we never know with the province, right? Okay, so we need to go all the way up to 450. So I'm going to go by 100 here. 100, 200, 300, 400, 500, okay? That's a pretty good scale. It needs to be consistent. Thank you, thank you. Anyways. This goes all the way to 30, right? So I have room here, so I'm going to go 5, 10, 15, 20, 25, 30. Okay, so you make the scale work. It needs to be consistent. It doesn't have to be the same along the axis, just consistent. So go up by the same amount. No zippers. Okay, you can't do the zipper thing. If you've done it in any other course, you're not allowed to do that here. So 450 is right about there. 1573, 15 is here. 73 puts me right about there. Close enough is good enough. And then 30 is at 11. So watch, I'm going to get rid of that line that I made there for 30. I'm just going to make that really close but not touching. That is important. Do not touch the x-axis. What do we call that? What is along asymptote, right? There's a horizontal asymptote here. And it tells us to stop there, or at least make a graph for a time of 30,000 years. I think that this should have been more specific. It stops being accurate after 30,000 years, or it's just asking us to make a graph, so we'll just stop there. But arrowheads would probably be okay in this case. So if you do add an arrowhead there, you can do that. And my equation. You don't need a title, but you do need the equation. There you go. So that would give you a 3 out of 3 on a graphing situation. And the province always gives you a grid. So you're never going to have to make your axes with a ruler. They give you a grid, so because we want nice graphs, okay? Okay, so that's it, okay? So how did I start this whole journey? I tried to see this on my calculator. I knew this point right off the bat. They told me to go to 30,000 years. I found a point in between to help me generate that curve, and you're good to go, all right? B is asking for what age of the object would give a concentration of 100 ppm. Basically, what is the age when the concentration is 100? It just makes it so much easier if you can boil it down to that. And how do we find this? We let y2 is equal to 100, second trace intersect. So let's go and see if we can find it. This should not be a problem. I am fairly confident that my window will show this. y2 is equal to 100. There it is. It's at that intersection where I'm going to find my answer. Second trace intersect, enter, enter, enter. And there it is. X is equal to 12.43 ppm. Parts per million. Okay. C. Yeah. That's X. Oh, I'm supposed to use Y, right? Oh, yes. Yes, yes, yes. Concentration is 100. I found my, sorry, guys. Yikes. Pay attention, right? Pay attention. This is thousands of years, okay? So I believe you would be fine there if you wanted like an actual, the actual year you would multiply this by 1,000, so that would give me 12,433 or 34 years. 12,433 years exactly. You would be fine either way. If just make sure you put the thousands of years after, and then you're fine. C is asking what concentration of C14 would an object that is 20,000 years old have? Okay, so can I put 20,000 in here? Nope, I gotta go 20, okay? So if they say 20,000, if that's the number, then you need to go 20 here. So 20,000 over 1,000. You need to go 20 in this case. So you wanna know what the concentration is. Okay, so how do I find that? I'm gonna clear Y2. I'm going to go second trace 1, X is equal to 20, so that's 40.04. 40.04 ppm. Okay, so that's, and you could actually use this to graph now too if you want to check when x is equal to 20, I'm in the 40s. So you could kind of embed that into your graph. But remember, close enough is good enough and applied. So that's how we roll, okay? Except for certain points, like the 450 must be on the 450, right? There's no, there you have no room to be off by, but everything else is kind of, as long as it's close enough, you're good. Is that good? Are we, I'm going to stop here. If there's a doubling time situation, if the doubling time is 10 years, let's say, then your population doubles at that time, at that rate, at 10 years, every 10 years. So 10 years go by, you need to start with 0, okay? 0, 1,000, that's my initial population. 10 years go by, this would be 2,000 because I double. Another 10 years go by, you double the population. So the doubling happens here, not on this side. Here you just go up incrementally by the same amount. Okay, here you're doubling, so you're growing much faster on this side. If it's half-life, we're talking a decay situation. So if the half-life is 2 hours, let's say, and you start with 8,000, so times 0 is 8,000, 2 hours go by, you're down to half of what you had before, and so forth. Another 2 hours go by, half of what you had before. So that's a decreasing scenario. Okay, so that's something that I would want you to understand as well. All right? Yeah. 19? Sure. Page 19. Don't clap yet. Could be bad. Right? Go. Yeah. So sure. This will be a good example. This should get you ready for the AC today. Okay. AC is a small quiz. The nuclear disaster of Fukushima, Japan. This is on page 19. Released a significant amount of cesium-137 into the oceans. The half-life of cesium is 30 years. That is a very important fact there for us to consider. If the initial release amount is considered to be 100%, so initially you have 100%, right, full concentration, create a table of the percentage of cesium remaining for 120 years. What's happening there? Well, you knowing that you have the half-life should give you a hint here. First hint should be, oh, I'm in exponential territory, right? And half-life, it's going to decrease. So I've got my time, and I've got my percentage. So at the very beginning, I have 100%. 30 years go by, I'm down to 50%, right? It's always half. Another 30 years go by, that gets me to 60. I divide this by half. Again, it's 25. I'm at 60 years at this point. Keep going. Another 30 years go by. I divide my population, or my percentage in half. That's 12.5. And because the question insists I got to go out all the way to 120, I have to do this one more time, right? So 30 years increment every time. You divide this in half. What am I at there? I'm not, today's a bad day for mental math for me. 6.25. Okay, so you've got the percentages as follows. You went all the way to 120. How many do you need minimum to do a regression? You need at least 3, right? So you need 3 points for a regression to work. But this question asked us to go to 120, so there we go. Determine the model, the equation that models this decay. So this goes into L1. This goes into L2. And then we're going to go stat, calculate exponential regression.
Excuse the interruption. Anna Guzi, please come to the office. Anna Guzi to the office, please.
Okay, so stat, we go to edit, we clear whatever is in those cells. You go to the top, hit clear, and we enter 0, 30, 60, 90, 120. And go over to the other side. Everything good. I check, I double check. No decimals missing. We're good. Stat, calculate exponential regression, call it. Then we feed it L1, so second 1, comma, second 2, comma, alpha trace to call Y1. Right, so that's going to paste the equation straight into Y1. Why is it so Minecraft-like pixelated, eh? Anyways, enter. There you have it. So we can write down our equation. 100, 0.9772. You can do 2 decimals, that's fine. That would be 0.98. But you can do more. So to the power of x. And what do I know? Can I tell this is decaying? Yes, is less than 1, so it's going to go down. By how much? Decays by, I'm going to do some math on the side here. I go 1 minus 0.9772. That is 0.0228. If you multiply that by 100, it's 2.28% per year. So if you ever want to know the per year amount, you get it from your equation. We know that every 30 years it will go down to half of what it was before, but if you want the yearly amount, in this case, you can get it straight off of your equation. Okay? Are we good there? Or do we need to, do you want me to do the whole thing? Kamalji? The whole thing? The whole thing. We got the equation, so this is good. C, what percentage remains after 50 years? So 50 years, it wants the percentage. That means that we need to use second trace value. X is equal to 50. And I'm going to now make sure that it actually shows up on my calculator screen, right? So let's see here. Let's hit graph. It's not a good one. Oh, we could have done our zoom stat, right? Zoom stat, but I need to have plot 1 turned on for it. I'm going to go zoom stat. Beautiful. Look at that. Will 50 fit in here? I don't know. I'm going to go window. My X max is 132. It's going to work for me. Second trace value, X is equal to 50. And Y is equal to 31.498, which rounds to 50. And that will be percent, right? We're talking percent. So 31.50 or 0.5% is going to be remaining at that point. D, how long will it take until 10% remains? How long until 1% remains? Okay, let's try that. So it's basically saying how long until you only have 1%. Oh, sorry, let's do 10 first. For that one, I need to go y2 is equal to 10. Second, trace intersect. That's part of your work, okay? Telling me the keystrokes. y is equal to, y2 is equal to 10, graph it, it's at that intersection, second trace intersect, enter, 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 and it is 60. X is equal to 60 years. Sorry. It says guess. I forgot to hit enter one more time. That can't be. I'm like 60. It says 25 right here. Why is it 60? There you go. It's 99.66 years. Couldn't I say 100? Not in applied. Not in applied. What if it's 1%? y2 is equal to 1, second, trace, intersect. Graph. I may have to increase my window. Probably, right? It's not meeting on the window, so you got to keep going, chase the curve to the right. So I'm going to go window, X max. What should I go with? I'm going to go with 300 for now. Sorry, not 3,000. Maybe I feel like I picked this one because it's going to make you go way over. Let's try this. Second trace 5. Enter, enter, enter. Oh, it found it. So it's 199.32 years. So to go from 10% remaining to 1%, it's going to take you almost another 100. It's going to take you another 100 years. Right? So to completely eliminate it takes a very, very long time. Okay. We're good? Okay. I feel like I'm